So I've just finished the A equals QR lecture. So the big ideas there start with the idea of a QR factorization. So when we say A is Q times R, what we mean is that A is any M by N matrix, Q is any M by R matrix, where R is the rank of A, and more importantly, Q has to have orthonormal columns, which means that the columns are mutually orthogonal and unit vectors. And then finally, R as a matrix has the same number of rows as A has rank, and then the same number of columns of A, and R is an upper triangular matrix. And so ultimately what we saw is that, to say that the columns of Q are orthonormal is the same thing as saying that the Gramian of Q is the identity matrix. So this gives us a quick way to check whether or not a list of vectors is orthonormal. And that's exactly what I have pre-written here in some code. So this first little bit of code will quickly tell us whether or not a list of vectors is orthonormal or not. So here, if we just define our list of vectors as I've pre-written here. So here I've written down 1, 2, 3 vectors in R4. And the code will put those vectors into the columns of a matrix Q, and then check whether or not the Gramian of that Q equals the identity matrix. So let's click evaluate and see what I have pre-written. So the first thing that prints out is just what we input. So this is telling us that the vectors that we input are the columns of this 4x3 matrix. Then the code will put those vectors into the columns of a matrix Q and calculate the Gramian. And here we see that the Gramian of that matrix is the identity matrix. So the answer to the question of whether or not the vectors we've input are orthonormal is yes, because we got the identity as the Gramian here. And we see that it's not difficult to derail this. So if I just change this like 0 in the last entry of the first vector to like a -11, this will throw off the whole calculation. So let's click evaluate and see what happens there. So now I've made a small change to the list of vectors, but when I put this new list of vectors into the columns of a matrix and I look at the Gramian, I certainly do not get the identity matrix. So the answer to the question of whether or not these vectors are orthonormal is now no. So that's what the first calculation cell here does. It effectively makes it easier for us to check whether or not a list of vectors is orthonormal. And then why are QR factorizations so useful? Well, I gave 2 reasons for this in the lecture. The first reason is that they simplify projection problems. So if you want to project onto the column space of A, you have to find a basis of the column space, you have to put that basis into the columns of a matrix called X, and then you have to apply this complicated projection formula, which is complicated because you have to invert the Gramian of X. However, if you have A equals QR, the projection formula dramatically simplifies, and all we have to look at is Q times Q transpose to look at the projection onto the column space of A. So in the code I've pre-written here, what you can do is if you have a QR factorization, you can input the matrix Q, and then you can input the matrix R, and then this will calculate the projection formula for us using the QR factorization. So I've input a matrix Q here, and I've input a matrix R. Let's see how this evaluates. So the first thing the code will do is it will multiply Q times R together to check that we get the A that we are particularly interested in. And then it will also print out Q and R to make sure, so we can make sure we input our data correctly. And it tells us that, well, projection onto the column space of R matrix A is given by Q times Q transpose, which is this particular 4x4 matrix here. This is the same example that I did in the lecture, so you can check that my lecture is correct by using this code here. And then the second reason that I've argued that QR factorizations are useful is because they simplify least squares problems. Normally, the least squares problem is Gramian of A times X hat equals A transpose times B. But when we have a QR factorization, the least squares problem simplifies to R times X hat equals Q transpose times B. And I call that a simplification because the matrix R there is upper triangular, and we can quickly solve the simplified least squares system with back substitution. So in this code, you can I've predefined a matrix Q and then a matrix R, and then I've input a vector B. So if you're working on a problem, you can adjust these definitions as necessary. And then let's see what happens when we evaluate this code. So again, it will multiply Q times R together to give us the matrix A we're interested in. And it will also print out Q and R so we can verify that we input our data correctly. And then the first thing it will tell us is, well, here's the original least squares problem. So here our matrix is 4 by 3. So our original least squares problem has a coefficient matrix that's the Gramian of A, which is a 3 by 3 symmetric matrix. And then now we're augmenting with A transpose times B here. But the next thing the code will print out is the reduced least squares problem. The reduced least squares problem has coefficient matrix equal to R. And again, this is nice because R is upper triangular, as we see here. And here we're augmenting the matrix R with the vector Q transpose times B, which is 1, -7, 1 here. This is the example we did in class. And in class, we went through the back substitution to solve for x hat. Here, I go ahead and just give the reduced row echelon form. And you can see that x hat is 1, 0, 1, which is exactly what we got when we did the back substitution in class. So hopefully you find this code helpful. And also, I hope that it sort of reinforces these reasons that I'm arguing that QR factorizations are so useful.